Good night from Bloomington. It's a wonderful day outside, so let's start with a quick check. Can you see me? Can you hear me? Okay, yes and yes. Thank you, Nathan. Thank you, Ryan. Okay, let's wait for another minute before we start. Other students may join us, but how are you doing? Are you enjoying the nice weather outside? You as well? So in Bloomington, right? I really miss this weather, but you know, this is spring break. It's all like a ghost town now, but I enjoy being here all alone with myself and having fun with econometrics, and hopefully you are having fun with econometrics as well. So how are you doing with the homework so far? It's a group work, right? So I want you to apply rules of statistics as we reviewed last time, but are you doing fine with the homework? The deadline is tomorrow. Any quick questions? Pretty good, all right? Because the whole idea of the first problem set is how to apply this basic statistics. Okay, Nathan, why don't you email me, all right? I may help you with, right? I certainly would assist you, but of course, I'm not gonna tell you the answers of the homework. That's not the point, but I will assist you. But send me an email, please. All right, I will try to do my best. Sure, just email me right away, and I will be prompt and I will help you right away. Okay, if you are ready, I'm ready. I have my water with me, and in this spring break Tuesday, I will be reviewing the simple regression model with you. You have been reading the regression model, right? By the way, the business econometrics is one of the most difficult courses in the program. So I think it's totally fine if you're struggling, but here's my promise. I'll try to make it simple or keep it simple with my simple exercises and simple logical approaches, and try to give my examples in the simplest form and give you the intuition as well rather than the math, because I can assure you that in the midterm or the final, I will not ask you about any proofs or any mathematical approaches to the properties of the regression models, but I will try to explain you how we are reaching the conclusions. So are you ready? Shall we start? Okay, let's do this, Ryan. You can see my slides, right? So let's start with a quick review of what we did last week. Last week, right, we studied the statistical properties of random variables, and we defined the expected value, the variance, which we will use today, right? And I tried to explain you how we transform a normal distribution. And why is normal distribution important? Because the central limit theorem suggests that the true value of the mean of the population tends to go to the expected value when we have many samples from the population, right? Randomly chosen samples. So that's why when we observe the means, these means must be distributed normally. And if we transform the normal, we have the standard normal, then we can build confidence intervals and test some hypotheses, checking if our parameters are, the estimated parameters are right or wrong, which I want you to do in the first problem set. Then this week, right, my plan is to show you the difference between correlation and causality. And in fact, many of the cases, the practice is finding the correlation, but it's totally wrong. Maybe you have been doing correlation in your work as well, but it's totally wrong, because correlation does not mean causality. And we are looking for causality in this course, business econometrics course, rather than if something is correlated with something else, but if one thing is causing the other thing, right? So I'll try to tell my point with an example, and I'll keep my example very simple and try to show you the simple regression model. The model is called ordinary least squares. So we're gonna ask one question: why is this model called OLS, ordinary least squares? And we're gonna estimate the parameters, right, as alpha, as beta 0 and beta 1. And then I'll try to explain some characteristics of the model, key assumptions that makes the model, And we're going to work with Excel during the last part of the lecture, and I'll go over the data set you have been working. There are two data sets on the modules, corn and GPA. So I'll work with the corn example, and I'm going to use Excel to analyze the data, and I'm going to use the Excel sheet, also some Excel data analysis property. But let's start with the one question, right? What are we doing here, right? In this business econometrics course, what are we really looking for? We are looking for the causality, right? What causes what? In a way, try to understand the predicted value of one variable, such as like quantity of cars to be demanded when the price of car is changing, right? One to another. And we're gonna write the model of that prediction. But at the end of the day, our goal is always to see if our prediction is the right prediction or not. But let me ask you my question, right? My favorite question. Can we predict 100% all the time, whatever the true value is? Can you tell me yes or no? No way, right? So can you tell me what our goal is then? If we are predicting the value, if we cannot predict the true value, what are we trying to do? Can you tell me very short? Get close. How close? This alpha close. You remember the hypothesis testing with your alpha, 95% sure or 97.5% sure? Exactly what we are trying to do is trying to keep it as close as possible, right? That's the idea of confidence intervals. But causality, right, is different than correlation. Even though sometimes mathematically it gives you the same approach, causality is something different than correlation. For example, what I have here on the slides is, right, it's coming from a website which is very kind of famous on the weird correlation things. We have read US spending on science, space, and technology, and the data correlates with suicides by hanging, strangulation, and suffocation. It's basically saying if US is spending more money on science and technology, people are committing suicides more and suffocate more. That's the correlation. But does that make sense? Is it really the same? Like, is it really the main cause of the spending or suicides? I'm picking up some, oh, let me, yeah. I did not adjust for that, right? I'm gonna mute all right? If you wanna speak up or if you don't wanna write, just you can unmute yourself. But is that better now, Ryan? Okay, perfect. So we're not, from a correlation perspective, right? We can tell a story that is telling us how US spending is basically killing people. But that doesn't make, does it? It's not our really model here. So correlation is important, but not the main thing. Another example, and this is a weird one, divorce rate in Maine, and it correlates with per capita consumption of margarine. So from a perspective, right, one correlates with the other, and one can say, if you don't want to divorce, then maybe you should eat more margarine for a happy marriage. And you can basically tell that story and convince people, right, showing the data. But data work is not enough. Showing the correlation is not enough. We have to prove with a model that shows us causality rather than the kind of correlation. So how to do that? We're gonna do what? We're gonna check the following, all right? So let me try to show you from this example. We're gonna write down a model that one is a function of another, like the, let's say the marriage, right? Like you're gonna get the marriage, let's say marriage as a function of the per capita consumption of margarine. Let's say beta 0 plus beta 1, times margarine. Maybe I should write here. Is this a better way to write this? Can I type here? Can I insert text? I never tried, but yeah, I can. Okay, so here's what I'm trying to do, right? Margarine equals to beta 0 plus beta 1 times eating margarine. Okay, so if I try to see this model makes sense or not, here's what I want to do. I want to estimate the parameters, beta 0, beta 1, and see if this beta 1 is 0 or not. How can I check if that beta 1 is 0 or not? Can you tell me? Now that you know about some statistics, right? And you're working on the problem set, if I want to check whether this beta 1 is 0 or not, what would you do? By the way, these beta 0 and beta 1s are the random variables we are trying to predict. Yeah, marriage. This is not margarine. I'm sorry. This represents marriage. Marriage equals to, it's 1 or 0, right? Marriage is 1 or 0. It's beta 0 plus beta 1 times eating margarine. So how can I check whether these parameters are 0 or not? That's the whole idea of the regression model. Can you tell me? It goes back to the last week. Okay. Let's add here. Check if beta 1 is 0 or not. Exactly. This is exactly the hypothesis testing, right? That's why I wanted to review hypothesis testing, because if there is a causality, hypothesis testing will tell us whether there's a causality or not. Okay. Plus uncertainty. It's that uncertainty. Yeah, that's right. Comes with the model plus u, and that's the noise, right? In fact, we're going to build our model on that noise. I didn't want to say it right now, but you're right, Jenny. We need to put some unexplained parts. And that unexplained parts will be represented as the error term. And we are going to build our analysis on these error terms. But this is the idea. So here's what I'm going to do. I'm going to start with the data. I'll show you the data and some kind of arguments from the data, and we're going to build the model. But is it clear why correlation could be not causality? And what we are looking for when we say causality? We are looking for a functional form. All right, any questions so far? Oops, I don't want to insert text anymore. Okay, let me clear. So let's start with the data. Let's say we have the price, okay, given at different price ranges. It ranges from 0.5 to the highest 2.3, and you see that the quantity sold. And suppose you are selling corn at the farmer's market, and each week you randomly change your price, but randomly, okay, that's the key point. You are not deciding and endogenously, but you are choosing the price randomly, and you are observing the number of your sales. For example, first week, you charge 0.75, you sell 35. Then 2, but your sales drop, 1.15 to 43. And these are the observed randomly chosen points. We have one parameter as our price and the other parameter as quantity sold. Now, we would like to know the causality, right? So the basic question is gonna be, how does quantity demanded for my product change with price? Why with price? So why is the question like that? Because I'm choosing randomly the price, right? I want to see the impact of my random decision, price, on quantity. So I want to write quantity as a function of price. And by using the model, I'm going to find that function in terms of price. Okay, given the data, here is how we can find the correlation or correlation coefficient. Now, correlation is from the population, we can find the correlation by the covariance divided by the standard deviation on X and the standard deviation of Y. We know how to find those because these are basically the statistical parameters, right? We studied last week. And from the sample now, the thing is, we don't know the population, right? We only know the sample. So instead of sigma x, sigma y, we're going to use the sample standard deviation of x and sample standard deviation of y. Now, the correlation coefficient is going to be between -1 and 1. But when it is 0, that means one thing: there is no covariance, which means there is no linear relationship between x and y. And if there is no linear relationship between x and y, right? No linear relationship, then there is no way we can find even causality, right? So that's a one-way thing. We cannot really understand causality from correlation. But if there is no correlation, there is no causality. So correlation must exist. So it's a one-way street. It's not a two-way. We need correlation still, but it doesn't mean that there is a causality. That's why correlation is not going to tell us the everything, because we are going to calculate correlation and correlation kind of correlation coefficient -0.86724 from the data we have, but that's not enough. That's only telling us there is a negative linear relationship, but it's not telling us exactly what that linear relationship is, because we need to know the prediction. Because I need to know the following: the next week when I go to the farmer's market, if I want to charge $1 or $1.15, I need to know 95% sure that what my sales is gonna be. But then my question to you is, it's more like a business question though. Why is it important to know the exact number of sales, or 95% sure of the number of sales? Why is that important? Now, think in terms of business now. Let's think in terms of a bigger scale, like you are gonna produce trucks or SUVs, right? You're gonna sell next year SUVs and trucks, and you know what price range you're gonna charge. If you know, not the exact demand, but if you know how many SUVs and trucks you're gonna sell the next year, how would that help you? Can you tell me? This is, again, a little bit economics for managers. Exactly, right? At the end of the day, you want to maximize your profits. And if you know how many SUVs and trucks you're gonna sell, you can plan ahead, you can organize ahead, so you don't overproduce, oversupply, and keep the supply at the optimal, and then you maximize profits. It's kind of not our concern, but it's the unitary elastic point, right? You want to produce where the demand is unitary elastic, and then you want to predict really if you're at that point or not. Okay? And in fact, this is one of the reasons now why car companies are building more and more. Car companies are investing on more and more bigger cars, SUV and trucks, and not smaller cars. In fact, it's something I discuss in my MBA course, right? These manufacturers are focusing on not smaller cars anymore, but SUVs and trucks. Like Ford. Ford just announced that there won't be any Ford Edge. Not Edge, I'm sorry, like what's the small, like Ford Focus, right? The smaller sedans. And also GM is not gonna produce, and Honda is dropping Civic. Why? Because probably they predicted that within the given range of prices, the demand is not enough. And they're using these regression models to understand what the next year's demand is gonna be. So knowing the coefficient does not do this for me, because here is what I'm really shooting at. Again, if I tell you a price to charge, right? Wouldn't you like to have an idea of the quantity you expect to sell? That's the whole idea. Okay, now a thought experiment. Please follow my points. Suppose you bring corn to the market and I set the price. The difference is you don't know what the price is gonna be, all right? You come to the farmer's market, and as a controller, I give you a price, but you don't know what the price is. You have no idea what the price I will set. What is your best guess as to sales that day? What would you tell me? Like, you're gonna bring some corn, like you have this data, right? You have this data. You don't know what price I'm gonna tell you, but you need to bring some corns to the market, right? what is the best guess you would make? Exactly right. That's what we studied last week. If statistically you are taking a random variable price, then you predict the outcome. The point estimate is the mean. So you take the average, and the average is gonna be the mean, like point estimate. That's how many corn you wanna bring in. But of course, it's not realistic, right? The price that you will know ahead of time. So you're gonna basically know the price before you bring the corns to the market. So you're gonna make a best guess depending on the price that you know. That's why we need to write the model in terms of the price and then predict in terms of the price rather than take the point guess only. Then that guess, that prediction will be more robust. Okay, here's what we're gonna do. When we know the price, that helps us for sure. So we're gonna write the simplest relationship ever between the two variables, which is a line. And that line is gonna be in terms of one parameter y and another parameter x, and writing down y in terms of x as beta 0 plus beta 1 x is the linear model. And this is gonna be like, if we have y here, if we have x, it could be like this or like this, depending on the slope, right? That's why we call beta 1 as the slope. If beta 1 is positive, then that is the case, right? Positive slope. If negative, then that's the case. So predicting these intercepts and the slopes is going to tell us the shape of the line and how fast or slow the rate of change is going to be. And we're going to call beta 0 as the intercept, which is going to tell us whether the point is right here or the point is right here. And then beta 1 is the slope. But let's go back to our example, corn and the price. Which one is y and which one is x? Can you tell me now? Now, if I want to write down my model, price is x. That's very important, right? Because that is all how we are going to set up our model, which is the causality effect. What causes what? Is the demand caused by the price, or the price is coming from the demand? Since you're going to make the decision on price, or you know what the price is going to be, right? The random variable, the one thing you're going to observe is going to be, it's not so random though, right? It's a functional form of price, so it's not random anymore. But the thing you are going to observe is the quantity. So we're going to write down the model as the following. So we will have as y, we will have the quantity corn equals to beta 0 plus like beta 1 times price. Now, I'm not adding that u term, right? I'm not adding that uncertainty there or undefined things in there, the error term. Because right now, what I'm assuming is if this is what the population is, I can tell the exact values. But we don't know the population, right? We're going to extend our analysis to the sample, or I wouldn't say extend, but we're going to work with a sample rather than the whole population. That's when we need to add the U term, the uncertainty term. So my point is, when we have the model y equals to beta 0 plus beta 1x, it can be, but it's going to be an incomplete model. Because with this model, you are expecting that you are going to predict perfectly. But we cannot predict the perfect quantity because we know that we are basically predicting the mean, right? And that mean is normally distributed, and there is always an error. So we have to take that error term into our model. And we're going to call that error or noise the random variable or a random variable u, the unexplained parts. What can be an unexplained part? I wrote something like such as weather or competing events or other things even, right? Just if you are selling corn, how many other competitors there? Or is it a kind of a good economy or not, right? Do people have money or not? So there are many so other factors that may be in, but it's not our model, but are gonna be explained by the unexplained parts. But you see how that creates a problem, right? Even that does not sound well, but the weather plays a huge role if you are selling something in a bazaar, in a market. Why? Because if the weather is shiny, nice, then you'll see more people in. If the weather is not, the less people in. And here is the problem with the simple regression model. You may need more parameters and you may need more observations. But let's keep that for the next week, right? Let's start with the easiest model and let's keep all the other factors out of our equation right now. So for now, we are only working with one parameter, like the price, to determine our goal, quantity sold. But of course, there are many others. So we're going to account for the noise. And the right model is going to be the y equals to beta 0 plus beta 1x plus u. But again, our y is quantity, x is price, and u is the unexplained part. And this is what we call as the simple linear regression model. And I wrote down the terminology for you. Y, that's one thing we called as the dependent variable. X is the independent variable. So here in our model, price comes independently, right? But Y depends on X, so Y is dependent. U is the error term, and we're gonna call beta 0 as the intercept parameter and beta 1 as the slope parameter, okay? So before we continue with the simple linear regression model, any questions about what the model is or how the model looks like and what we are trying to do? Any questions up to this point? I'm trying to keep it simple, but is my example making sense to you? Of course, you can extend this example to any other basic managerial question, right? This is quantity price, but you can extend this to any other decision, like, you know, quality versus your price or other things. Does U represent single error term? That's a very good question. And U represents the unexplained part. Now, we have many data points, right? And this U is going to be different for these data points. This is the linear term. And when we have the estimation, right, we will end up with the estimated line. And on the estimated line, U is going to be 0. But expected values of U's will be 0. That's the reason. So there is not only one U, but there are many U's. There are many unexplained parts of each data. Let me go back to the data, and I'll show you what I mean. Like if this is the data, right? There is one U for this after the estimation. One other U, another. So we will have 1, 2, 3, 4, 5, 6, 7, 8 unexplained parts. But we're going to assume one thing. If we have all these 8 unexplained parts, if we are estimating right, the sum of all these unestimated parts will be 0. That's how we're going to build our model in. Okay, Paul, does that answer your question? Okay, so that U is the part that we are not explaining. But we're going to put some restrictions on it. That's what we need to do. Okay, so... Okay, if we believe in our model, that's how we start our estimation. We're going to say, this is the model. We believe in our model. We would like to use the data, samples, right? The data is coming from a sample, to estimate its parameters. Which parameters? We are estimating beta 0 and beta 1. So we would like to know how Y is changing, like how quantity is changing when there is a change in price. Or if I know what the price is, Y is going to be the best predictor of the price, best predictor of the quantity. And that's what I know. Like if I tell you that you're gonna charge $5 next week, then you know how many corns you need to bring to the farmer's market. That's gonna be your best predictor. And that's what we are looking for, the best predictor. And the conditions that we're gonna list is gonna basically tell us statistically that Y is gonna be the best predictor of, or OLS model is the best predictor of Y. Okay, best predictor, that's our job. Let's specify the model. We need some assumptions to start with. Assumption number 1, which is very important. We're gonna assume that expected value of the use will be 0. So here's what we are trying to do. We are trying to estimate, right? So what we're gonna say is our point estimate is the mean, okay? The point estimate is the mean point, which is basically saying that if you get the mean point of Y, like, let me write here, like mean point of Y. So let's say Y is the quantity, right? And X is our price. From the data, if I know what the expected value of quantity is, oops, there's a bar here, and I know what the expected value of the price is, which I know, right? Basically, these are the averages because it comes from the sample. Then what I'm claiming is I'm gonna build my line, which price is here, quantity is here. I'm gonna build my line so that my line is gonna pass through this point where we have the mean, P bar, and Q bar. So my line is gonna pass through this point. What I'm trying to say is means must be set of the best predictors. So the line that I'm gonna find as the best predictor must have the mean within. But how many different lines can pass through one point? Can you tell me? It's a basic calculus question, but do you remember? Like how many different points can pass through one point? This is one point we want the line to pass. Like this could be like this line, right? Or this line. Oh my God, I'm not a very good artist. Or this line, or this line. Infinite, right? That's right. That's why we have to pin down our line with some assumptions. And in order to find that, this is our first assumption. We want to measure how far each point is from our line, okay? Like if your point is here and your line is here, the difference between your point and the line, or how far that point is from the line, is U, the unidentified part. And there will be some U's. We want the sum of these U's to be 0. Let me show you, like, if this is my predicted line where the average is here, then there will be other points here, 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 here. I want the distances, when I add all these distances, which are U's, to be 0. And that's my assumption. And that's gonna pin a lot of things. And then we will try to find the parameters and have that line figured out. And that's gonna be our regression line, okay? Is my logic making sense to you? Because I'm trying to put the context into logic, all right? Because the math is a little bit more complicated than this. Okay. And in fact, I try to explain here on the slides, this is a very benign assumption. If you assume that the expected values U is not 0, but some constant K, then you can always move the line K to the right or left, depending on the positive or negative sign, and then still get the expected value as 0. So it doesn't matter really, because what you are doing is you are finding the beta 0, which is the intercept. So this is pinning out the intercept. I know what the intercept is gonna be, but here's the thing. If I'm pinning the intercept and the mean, if I know the 2 points on a line, can I figure the line out? That's again a basic calculus question. If I know 1 point as the point of means and the other point as the intercept, can I figure the slope if it is a linear curve? Exactly, right? That's the whole point of the model. Then we're going to figure what beta 1 is going to be depending on beta 0. Then the question becomes how to figure the beta 0, right? Because if I know what the beta 0 is, I know beta 1 is. I wish there are more easier way to say this, but I am really hoping that I make sense, because the assumption here is this is last week's topic, right? You have already read this stuff and you know some of this stuff, what I'm talking about. Otherwise, this may not that making sense to you, but when you read, when you know what I'm talking about, it makes more sense. Okay, assumption number 2. This is also a very important assumption. We have expected values of u's 0, but we are going to have also expected value of the undefined, the unexplained parts given x is 0. Basically, what we are trying to say is the error term is mean independent of x. If the mean of x changes, right? If the price of the mean changes, we will still get the same result. The u's will be still 0. So in other words, if I change the point, like, I kind of gave the example here. Suppose I tended to raise the price on corn when the weather was good, which means crops were bigger. Should I interpret the changes in quantity demanded with changes in price as the effect of a price change? No. What I'm saying is, if I increase the price when the weather is good, I'm moving the price average up, so quantity average is going up. That effect is not going to change the unexplained parts. The expected value of that unexplained parts will be still 0. So the true effect is being maxed by the changing crowd size. So there is some other unexplained parts that is masking the true effect. So that slope will be still the same. That's what I am trying to really achieve here. If I change the sample, if the mean of the sample changes, but still the slope remains the same. That's what this assumption 2 is for. Assumption number 4 gives us the intercept. Assumption number 2 gives us basically telling us that slope is not going to change even if you change the point, like the mean points. Given the 2 assumptions, we have the expected value of y. Given the data, we have x as beta 0 plus beta 1 x. Because here's why. Let me go back to the expected value of y given x is the expected value of beta 0, but expected value of beta 0. Beta 0 is just constant. What's the expected value of a constant? It's all constant, right? What's the average of it? It's itself, right? Beta 0. Then beta 1 times x, the expected value, it will be still beta 1 0 x, but the expected value of u given x will be 0. So that's why we will end up with the kind of the predictor. So expected value of y given x will be our predictor here. So we want, on average, right, how much corn will I sell when charging the given price? And that's the expected value, which we will call as the predictor of y. Now, we're going to rewrite the model. And we will finish now with the complete model. We have y, the true value, right? This y is the true value as the expected y given the set of prices plus the unidentified part. And we're going to call the first part as the systematic part. This part is the systematic part, which is the part that explained by x. U is the unsystematic part, which is the part not explained by x. Now, my question to you is, before we move further, these are 2 parts, right? Part 1, part 2. What if part 2 is way bigger than part 1? Is your model gonna really predict what the output is gonna be. Like, let's say part 1 is like 75%, part 2, and part 1 is like 25%, which means 25% of your real value is explained by part 1, and 75 is explained by the unsystematic part. Is my model gonna be robust? No. So what's the right way to approach this? So we want this part as small as it's possible, but this part is not gonna be 0%, and this part is not gonna be 100%. So that's how we're gonna find what we call as the R-square. R-square basically is gonna tell us what percentage of the model is explained by the systematic part, which we want, and what other percentage is the unsystematic part. And there is a mathematical way to calculate R-square. I will show it, but this is the kind of the intuition. R-square is the part, the percentage of the part that's explained by the systematic part, which we want. And as R-square goes up, we are predicting better and better. As R-square goes down, you are not doing better. So you have to find another model, or you have to find another set of data. So data is not explaining well what it is going on in the real world, because that's what the systematic part is about. Does it make sense? Since I can't see your faces, right? Again, when I'm teaching the MBA, right, I am giving all these concepts with some examples, and then I see their faces, and I try to read their faces because I am a poker player. Of course, some of my students are poker players as well. They stand still. I cannot read them, but I know how they feel about the concept. But since I cannot see you, right, I cannot tell. But at any point, if you have any questions, please type, okay? I will be reading and I will be answering your questions. Okay, now suppose we have a random sample, X and Y's, like price and quantity. If we assume the regression model, we have yi equals to beta 0 plus beta 1 x1 plus ui. We believe each observation is following this model. We're going to use the data to get estimates to the slope and intercept. So let's try to estimate them. Here is what we're going to do. We're going to define the fitted value. Here is what fitted value is. It's y cap or y hat. Cap is hat, right? The same. So hat, let me say hat. Y hat, yi hat. It's going to be the beta 0 hat, but why we have hat? Because this is the predicted value. And beta 1 hat xi, this is also the predicted value. So the fitted value depends on the predicted value of the parameters and the price. And the difference between the true value and the fitted value is the ui hat, which is the unexplained part. And we can calculate the unexplained part after we regress the data to find the exact fitted values. And I will show it to you in Excel in a moment. But that is what we will be after and check the assumptions. And we're going to estimate the parameters and see if the parameters are fitting the data well or not. Because if it is not fitting the data well, it's going to show. And that's not going to be the model we want. We want the models to fit well. Let me ask you another question. What if all these UIs are 0? Like you predict the line and you see that all UI hats are 0 for all observations. What does that mean? Good model? It's good. Exactly. You read my mind, Ryan. It's in fact too good to be true, right? It's basically the linear relationship, and it's not going to happen. It's never going to happen. As long as there is this error term, they are not going to form the linear curve itself. If it is always 0, that means you are basically observing the line itself, which is not going to happen, of course. Total function. And in fact, in that part, if that is the case, do you know what R square is going to be? You tell me, like, what's going to be the R square? 1, right? 100%. Exactly. We will have 100%. You get the idea. That's perfect. Okay, why are we calling this as ordinary least squares? Here is why. Our goal is to keep the sum of the squares as minimum as possible, and that's how we are choosing these betas. In fact, we already know what the sum of UIs are, right? Assumption number one, the sum of UIs are 0, but the squares are not going to be 0. By the way, why are we taking the squares, not the third, fourth, or fifth power? Can anyone like try to guess? Exactly, right? We do not want to make things to be complicated, so we don't need 4, 6, 7, 8, but we don't want third or fifth as well, because we want to get rid of the negatives, and in fact, we want not the value, nominal value, but we want the distance, right? The true value versus the line value, the fitted value, the distance. That's why we are getting rid of the negative values. Okay, so how do you solve a minimization problem? Have you solved any optimization problem, like in other courses, like cost minimization or utility maximization, these kind of things, like Lagrangian models? What you do is you check the first order conditions, which means you take the derivative of the objective function. Yes, but using Excel. Yeah, in calculus, how we do it is we take the derivative of the objective function with respect to the parameters. First beta 0 hat, then beta 1 hat. Then we come up with the equations, two unknowns, and we solve the unknowns depending on these two first order conditions. Of course, I'm not going to show you all. If you are really wondering, you can check the book, the whole math of it. It's basically solving an optimization problem. But we are minimizing the square of residuals. But as I told you, this is one way, right? There are other ways as well. And the other possibilities are sum of the residuals, but with our assumption, it's impossible because we are assuming that the sum of the residuals are 0, right? So that's not something you cannot do really with this model. Or sum of absolute value of residuals, that's also possible. Or sum of residuals raised to 4th power. But technically, all of these models have some notable drawbacks. And statistics researchers show that sum of squares will lead to the minimized errors. So they decided to go with the squares rather than 4th power or the absolute value of it. And then we estimate, we can write the regression line, OLS regression line. And this is also what we call as the sample regression function. If we know the data now, the best predictor y hat will be the predicted value of the intercept plus the predicted value of the slope times the observed value of x. And this is going to be how we are reading the prediction of y in terms of given x. So let me switch to Excel and show you how this is defined, okay, how this is kind of calculated given the Excel and also by hand as well. All right, so are you ready? I'm going to work with Excel now. I'm going to switch to my other sheet. So let me go to my other screen. Okay, can you see my Excel file now? Okay, so here's the data we have. We have the quantity and the price, right? So beta 0 and beta 1 are kind of coming from this optimization problem. You may have already seen it in the book, right? But what you want to do is first finding the means. How do you find the mean? Like mean price. Mean price is basically the average of the data, like B2, like the average to B2 to B9. Pretty straightforward, right? And mean quantity is the mean of the quantity observed. And you see that the average price you have is 1.34 and average quantity you have 37.5. And in fact, this is how we are going to build our analysis. the regression line must have this point on. So the point must, this point, 1.34 and 37.5 must be our line, must be on our line. Then what else to find? We need the covariance. And in fact, Excel has a covariance function within. So you can find the covariance and then the variance of price. Then how do you find beta 1 and beta 0? Here's how. You're going to find beta 0 depending on, no, let's find beta 1 first. Beta 1 is going to be the way we defined earlier. If you remember, it's going to be the covariance divided by the variance of price. And in fact, this is the solution of the optimization problem. All right, this comes from the OLS. And you can find the beta 1 as negative 17.4. And beta 0, which is the intercept, now that you know what beta 1 is, and you know these 2 points are on the line, then what you can do is you can find beta 0 by finding like E3, which is mean quantity minus beta 1 times mean price. So basically you are using the fact that the mean point is on the line, and then you calculate the intercept. Okay, what else do we have? Here's what we have, right? Fitted values. Fitted values are, you observe 0.75. Then we have the line. So this is what our predictor is telling us. Our predictor is telling us the value must be 47.72. But what we are observing is 35. So what's the difference? The difference is the residual, negative 12.72. And residual square is 161.82. Okay? So if we do the same analysis for every one of them, we're going to have the residual for every one of these points. And in fact, this residual is nothing but this U-turn, right? The unexplained part. And here is the good part. If I add all these things up, what's the sum going to be? What do you think? If I add all the residuals, that's right, right? Sum is 0. That's how the regression model works. And if I add the residual squares, it's not going to be 0, but we can claim that this is the lowest possible. And you cannot find a lower sum of residual squares than this. And that's what the model is going to tell us. Okay. And next part is showing how this model is really explaining, like R square, right? The systematic part, unsystematic part. What percentage of the model is explained by the systematic part, and what percentage is explained by the unsystematic part? But before I start working on that, let me go and show you how we use the regression function in Excel. You don't have to do this by hand, right? Here is the easier way. Okay, you go to data, you have data analysis, you click on the data analysis, and on the data analysis there is this regression function, right? So you click on it, and the Excel will ask you, what's your input Y range, and Y is the dependent variable, and my Y range is the quantity. What is your X range? My X range is the independent variable, which is the price. So I click on them, right? I click on this, and then I choose my data. Then I choose my confidence interval level if I want to make some hypothesis testing. Right now we are not doing that, but in the future we will. Okay, you need to choose confidence interval. Then I click on residuals. I'm going to choose my output range, and when I click on OK, here is the summary output. You see the intercept, which is our beta 0, is 60.77, and X variable, which is our beta 1, is negative 17.4. And voila, right? The same result. And the Excel will give you these parameters. And in fact, Excel will give you the predicted y's and the residuals as well. And it's exactly the same, right? This is what the Excel is doing for you. This is by hand. You can calculate all these coefficients like parameters and the residuals and residual squares, but Excel can tell you right away, which we will use in the future. But is it clear how we are running regression using Excel? You don't have to do it by hand. Have you tried? If you have not, please try with the corn data, GPA data, or the other data sets you have, especially the problem sets, right? Okay, any questions about the regression model? All right, perfect, thank you. Okay, now that we calculated the OLS estimates, are they meaningful? That doesn't mean that they're meaningful. We still need some assumptions about the model and sample to inject some meaning. And this is something we will do later. But we still need some kind of properties to be held so that these slope and intercepts to make some kind of a meaning. But for starters, here are some basic facts. Again, the residuals must sum to 0. And the second assumption, right? X times UI is 0. So if you check the price times U for every other pair, that's going to be 0 as well, which is basically telling you that the expected value of U given the prices is 0. These are the two basic assumptions. That's why we know these two statements are true. Third one, the point compromise of the average values of the independent and dependent variables always lies on the regression line. That's something I told you, right? So these three always must hold. How do you know? Because that's the fitted value. That's how we construct our model, in fact, the OLS. And the fitted value at X is going to be X, what? How do we know? Like, this is supposed to be Y bar, all right? Not X bar, but Y bar. Why? Because that is how, in fact, the whole model is built on, because the average is on the line. Okay, is this the best line? That's the key question. But we solved the parameters to get the best line for the data. But how good is this line? Again, the question becomes the systematic part versus the unsystematic part. Because the purpose of this regression is we want to know what the Y is going to be given the knowledge of X. That's how we are going to define the predictor Y. Okay, it tells us about Y, then the true Y's should be very close to our line. U's must be small, right? But if not, true Y's will often be far away from our line. So is it close or far? We can calculate how close or how far these numbers are. And that's what we call as the sum of square of errors and sum of square of residuals. Variation explained by our model is sum of squares of error, and variation not explained by our model is sum of squares of residuals. And R square, as defined as the ratio of the two, sum of squares of errors to sum of squares of total. So basically what we are trying to find is how well the systematic part is explaining and how well the unsystematic part is explaining. And it's going to be between 0 and 1. If it is close to 0, then our line fits the data very poorly. But 0 means the systematic part is not explaining at all. But if it is 1, the systematic part is explaining 100%. You may now guess what our goal is, right? Our goal is to keep this R square as high as possible. So that's sometimes what we're going to do in our models. We're going to keep adding or subtracting parameters to keep that R square high. But if it is 1, then we have the perfect linear relationship, but it's never going to be like that. Because when R square is 1, that means all our points are on the line, which is not going to happen, of course. So let me show you again. Let me share my other. Before I finish, let me show you this one more thing. Now you can see my Excel file, right? So what those things really mean? So we have the sum of squares of total. So it depends on, again, the mean price, right? Minus the, I'm sorry, like the price minus the mean price squared. The whole thing squared. So basically what we are looking for is how far, right? SST is which one? Which one is, Ryan? The distance from the line? The distance from the line, K? Column K. Yeah, column K is, okay, column K is how distant are observations on prices from the mean. So how distant from the mean, right? Squares. Yeah, from the mean. And then this is like price itself. So we're going to find SSR depending on the residual squares and sigma square as E11, like SSR is divided by 6. So what we're trying to do is trying to find the samples estimate, and then SSE is going to be 1 minus SSR divided by SST. So what is R squared? Okay, if I want to write R squared, it's going to be 1 minus SSR, which is E11, divided by SST, which is E14. Oops, sorry. So look, what do we have? 98.75%. Yeah, because I gave you the data. Probably that's why. It's not all random, right? I generated it. So this explains. Well, but we will be able to read R square no matter what, and it's going to tell you how well the data fits into the line. And our goal is going to be to keep that R square as high as possible. So today, what we looked into today, what we studied is that we studied the simple linear regression model, and it is basically we are trying to estimate the prediction of y, the dependent variable, given the independent variable. So we wrote down the functional form using the OLS method. We predicted the slope and the intercept, and then we tried to understand if the model is explaining well or not. Next week, I'm going to continue with the multiple regression model. Part 1, it's going to be a couple of weeks to study the multiple regression model with many examples, but simple regression model is the starting point. We will not probably use the simple regression model a lot because we are going to need a lot more parameters, like the quantity corn you are selling. It depends on the price, but also it depends on many other things, such as weather or the competitors' prices, or even like how the income of these guys are, right? Or even the location of the market. These other things are going to represent within the multiple regression model. So what we are trying to do is, you remember the U-term, right? The unexplained part. We're going to take more parameters from the unexplained part and put it into our model and try to explain even further what the real value of y is going to be. But that's next week. So here's what I want you to do. Finish problem set number 1. This is until Wednesday night. And then you start reading the multiple regression from the book. If you haven't done so, then next week when we meet on Tuesday, right? We will go over the multiple regression model again with using Excel, with examples, and try to explain you the logic, and hopefully we'll continue from there. How does that sound? Does that sound like a plan? Okay, perfect. And if you have any questions, meanwhile, please email me. I am checking my emails at least once a day. And if I'm away from the office, and if you're asking for a question, sometimes I'm not able to reach the documents, please state the question as well, and then I will be helping you. Is there a minimum number of observations or rule of thumb? The more you have, the better your line is going to be. The R-square is going to go up. But the minimum value is going to be more than the parameters you have. Like what? Like if you have an independent parameter and a dependent parameter, right? Like price and quantity, you have two. Then you at least need three. But three won't do it because central limit theorem suggests 30 or more. Like, so the more you have, the better it is, but you can still find a line. But the less number of observations you have, the lower the R-square will be. The less percentage of the true value is explained by the systematic part. That's what's going to happen. The bigger the data is, the more the closer the real value you'll reach, kind of. That's why we want the big data, right? The more the data you have, the better it is. Okay. Any other questions? I hope you enjoyed this brief 1-hour session of econometrics. As I'm repeating always, I'm going to repeat one more time. It's not easy to go over everything in an hour or so, especially in econometrics, but I am really hoping that I kind of try to give you a little bit less math, but more intuition on what we are trying to find with a very easy and simple example, but you can extend this to any data set and follow the same logic. You will be able to predict now. So if you have no other questions, I'm going to call the night. Good night from Bloomington, again, one more time. And I will be seeing you next week. Until next time, take care and have a good night, guys. Bye-bye.